Hello everyone. So in the last lecture we have discussed how to compute probability of intersection of two events or how to compute conditional probability, that is probability of one event given that the other event has already happened. Okay. Today we will be discussing some standard probability distributions. What do I mean by that? So far we have worked with different cases where we would know the probability structure. Now, there are some standard structures in which we can fit many things. For example, if I am recording whether a student is present or absent as say 0 and 1, okay, 0 for absent and 1 for present, then I could see at the end of year what is the proportion of days on which a particular student was present. Okay, suppose that proportion is 0.8. That would mean that I can make a statement of the type that probability that a student was present during this semester on any given day is 0.8 because the student was present on 80% of the days, and probability that the student was absent was 0. And I could then perhaps compare this with some other student or with some other class and see if probability of being present differs from class to class or whether it differs from student to student, etc. Okay, so whenever we have binary variables, we have seen different types of variables. So whenever we have binary variables, that is variable which can take only two values, we can model probabilities of that variable by something known as Bernoulli probability distribution. Okay, what is a Bernoulli distribution? So Bernoulli distribution is used when we have only two possible values like present absent, yes no, male female, etc. Okay, so suppose I have a random variable x which takes only two values. X can be either 0 or 1. We will say x takes value 1 with probability p, and then the remaining probability has to be for 0 because these are the only two possible values. So x takes value 0 with probability 1 minus p. Okay, then we say that x follows Bernoulli distribution with success probability p. This p is known as parameter of this distribution. Okay, because if you know p, then you know probability of everything, probability of 0, probability of 1, and of course probability of other things is 0. So this p is known as parameter of a Bernoulli distribution. Okay, this is generally called as success probability, but that just means it is probability of occurrence of 1. It doesn't have to do anything with the actual meaning of the word success. Okay, here success basically means event of interest. So it could be actual success like cracking some exam, or it could be the chances of dying in an accident, or it could be chances of contracting a certain disease. Okay, so whatever is the event of interest, that is called as success, and the complement of that is called as failure. Okay, so let me take some example. So suppose we have a set of disks. Okay, we have a set of disks. Say we have a set of 10 disks. Okay, and chances of a disk being defective, chances of a disk being defective are, let's say, 0.1. Then what does it mean? It means that when I pick up 10 disks, one of them is likely to be defective. Okay, because 10%. So one of them is likely to be defective. So the probability of disk being defective, zero point 0.1 here, will be success probability, because for us event of interest is the disk being defective. So zero point 0.1 is my P here. So I will say that if xi, we define xi to be 0 if ith disk is not defective. Okay, because 0 denotes opposite of the event of interest. So xi is 1 if ith disk is defective. Then the sentence that we wrote here tells me that each xi follows Bernoulli distribution with success probability zero point 0.1. Okay, with success probability zero point 0.1. Now, ideally, generally, we don't stop at single xi. Ideally, I would like to see what is the total number of expected defectives, or if instead of 10 disks, if I had say 50 disks, then how many defectives I am expecting. Okay, all that stuff. So, Bernoulli distribution will be useful when I am talking about single success or single failure. But most of the times, we would be interested in talking about multiple successes or multiple failures. So, in such cases, we have to go for another distribution named as binomial distribution. So, what is a binomial distribution? So, suppose I have these Bernoulli random variables. So, I have x1, x2, xn, each Bernoulli with success probability p, and we say that they are IID Bernoulli p. What do I mean by IID? IID means they are independent and identically distributed. Okay, they are independent and identically distributed. What does it mean? Identically distributed means each of them has the same distribution. Each of them is Bernoulli P. So for each x, the success probability is same P. And independent means what is the value of one variable that does not affect value of other variable. For example, in the disk case, if x1 is defective, that doesn't tell me anything about x2. X2 still has the same chances of being defective. Okay. So typical example for Bernoulli distribution is coin toss, whether it turns up head or tail. So binomial would be used if I want to model something like total number of successes or total number of heads in say n tosses. Okay. So if I want to talk about that, so total number of successes out of n trials. Okay, if I want to talk about total number of successes out of n trials, then because each xi is denoted by 0 and 1, I'll have to define something called as y, which is sum of xi's. Okay, because if xi is 1, then it has to be counted. If xi is 0, then it doesn't need to be counted. That would be achieved by y. Let me write. Suppose I have x1, x2, x3, x4, x5. I'm talking of 5 disks. First disk is defective, second is defective, third is not defective, fourth is not defective, fifth is not defective. So total number of defectives is 2, which is basically just addition of xi's. Okay. So total number of successes out of n trials is y equal to summation xi. Okay. Now, what are the possible values of y? If all xi's are 0, then y would be also 0. If on the other hand, if all xi's are 1, then y would be n. So the possible values of y range from 0, 1, 2 up to n. Okay. We cannot, y cannot take negative values and y cannot be larger than n. Okay. So in such a case, we say that y follows binomial distribution with parameters n and p, where n is the number of trials, okay, or largest possible value, and p is the probability of success in individual trial. Okay, so p is probability of success in an individual trial. And n is what? N is total number of trials. Now we can see here y takes only integer values, and that too values between 0 and n. Okay. How do I compute probability of each of these values? So for example, I want to compute probability of y equal to 0. Now y is equal to 0 means each xi has to be 0. So this is same as x1 being 0, x2 being 0, and so on, xn being 0. Okay. Now we wrote in the beginning that these xi's are identically distributed and they are independent of each other. So it would simply be product over I going from 1 to n, probability of each xi being 0, okay, and probability of each xi being 0 is 1 minus p. So this is 1 minus p raised to n, okay. Probability of y being 0 is 1 minus p raised to n. Similarly, probability of y taking value n, that can happen if all xi's are 1. So x1 is 1, x2 is 1, xn is 1. So this means I going from 1 to n, xi equal to 1. Okay, so this is p raised to n because each xi is 1. So chances of that happening are p. So p raised to n. However, things are not that straightforward when it comes to some intermediate value. So if I want to compute probability of y equal to k for some k which is not extreme value, that is for some k which is between 0 and n. So it is neither 0 nor n, it is somewhere in between. And of course k is integer, okay. K belongs to set of natural numbers. Then in this case, what I know is, okay, so if I have all xi's here, I know out of them k are successes. But the thing is, I don't know which k are successes. It could be first k, it could be last k, it could be first, third, seventh, ninth, and so on. Okay, so we have to allow for that possibility. So we know that there are k successes, so we have that probability p raised to k. It means remaining have to be failure, so 1 minus p raised to n minus k. And in addition to this, we don't know which k, so there could be any k out of n. Okay, hence probability of y equal to k is n choose k, p raised to k, 1 minus p raised to n minus k. What is this? N choose k. It is also denoted by this. This basically means how can I choose, what are the number of ways in which I can choose k objects out of n objects. Okay, let me think of, say, suppose I have only 3 xi's. Okay, my n is 3, x1, x2, x3. and I'm talking of two successes. So those two successes could be here, or they could be here, first and third, or they could be here for second and third. Okay, so what we know is that how many that the number of ways in which these two successes can be arranged is same as choosing any two xi's out of 3 to allot success. So same story here. We are choosing any k out of n, and formula for this is n factorial upon k factorial into n minus k factorial. I hope everyone remembers what factorial is. Factorial is product from 1, 2, 3 up to n. That is n factorial. So k factorial is product from 1, 2 up to k. And n minus 1 factorial is product from 1, 2 up to n minus 1. Okay. So probability of y equal to k is this. This is known as binomial distribution. If I continue with the disk example, what I know is that I have 10 disks, okay, and chances of each disk being defective are suppose 0.1. So my n is 10 because at most all 10 can be defective. Okay, so suppose x is the, okay, let me use y because we have been using y for binomial. Suppose y be the number of defective disks, y be the number of defective disks out of n. Okay, then what are the probabilities of y? So what are the chances that you have no defective disk in this pack? Probability of y equal to 0 will be 1 minus p raised to 10, that is 0.9 raised to 10. Similarly, probability of all being defective is p raised to 10, that is 0.1 raised to 10. Okay. In general, probability of let's say 3 disks being defective would be 10 choose 3, 0.1 raised to 3, 0.9 raised to 7. Okay. So, probability of k disks being defective out of k is given by 10 choose k, 0.1 raised to k, and 0.9 raised to n. N is 10, so 10 minus k. Okay. So these are the chances of k disks being defective. So in general, if someone asks you what are the chances of 5 disks being defective, this is what you give. Binomial distribution has lots of applications. Two of the important properties is expectation of y, that is expected number of successes is n into p. Okay, so in this disk example, it would be 10 into 0.1, that is 1. One disk is expected to be defective out of 10, which makes intuitively sense because we say that 10% of the disks are expected to be defective. Okay, so let me consider an example where binomial distribution can be used. Okay, so for example, someone tells us that the some disease is getting spread, okay, and someone tells us that the chances of a person having this disease are 0.001, and our town suppose has 1 lakh people staying in it. Then what is the expected number of people who will be affected by this disease. So that 1 lakh is my n here. Zero point zero 0.01, the chances of getting the disease are same as chances of success here. Okay. And what we know is for an individual person, there are only two outcomes, getting a disease or not getting a disease. So every xi is 0 or 1. Total number of patients in that town can be denoted by binomial. So y equal to summation xi, I going from 1 to 10,000. Okay. So total number of defectives will be y. This can give me an idea about what are the chances that say 100 people will be of if patients. Suppose you have a hospital with only 100 beds, then you would be interested in estimating what are the chances that more than 100 people would be affected by this disease. So you would be interested in something like probability of y being greater than 100. So this I can get by considering all possible values above 100. So k going from 101 till 1 lakh. And here I would have same thing. N choose k, capital N here, p raised to k, 1 minus p raised to n minus k. Okay. And what will be the expected number of people who get the disease? That would be this 1 lakh into 0.001. Okay, that is the expected number of people who will get the disease. Is it okay? So this is all about binomial distribution. But binomial distribution has one limitation. Binomial distribution can be used only when there is a clear-cut upper bound on the count. For example, in the disk case, we knew that we are talking of a single pack of 10 disks. Hence, the number of defectives can be at most 10. It can never exceed 10. Okay. Same story here. Our population is 100,000, that is 1 lakh. Then the number of people who get affected can be at most 1 lakh. It cannot exceed 1 lakh. Okay. So binomial distribution has limited range, or what is known as finite and bounded support. Okay, it cannot go beyond n. So if we want to count something which in principle can go, doesn't have an upper limit, then we will need another distribution. Some examples for this are, let us say, count of people visiting an ATM in a given hour. Now that count could be 0, that count could be 1, that count could be 100. And if it's a very emergency situation, then that count could even exceed 100. So there is no perfectly known upper bound that we will have on count of people visiting an ATM. So in such case, binomial distribution cannot be used. Okay. So we have to go for another distribution for count data, which is known as Poisson distribution. Okay. Poisson. Of course, Poisson is the name of a person, so P has to be capital. So this distribution is generally used when we want to model counts of rare events. Okay, rare events means it could be number of uh, number of patients of a very rare disease. It could be number of typing mistakes in a book from a well-known publisher. And typical examples of Poisson are number of people visiting an ATM, number of calls received at a call center, number of accidents, or number of insurance claims received by a company per day, etc. Okay. So Poisson distribution is also for counting things. So the range of values, so if x follows what is known as Poisson lambda, then range of x or support of x is actually starting from 0, 1, 2, and there is no upper bound. Okay. In principle, it can take even large values. Of course, we all know that in a situation like say ATM, very high values are almost impossible. So the probability structure allows us to make those probabilities near zero. Okay. So probability that a Poisson random variable takes value k is given by e raised to minus lambda, lambda raised to k upon k factorial. Now you know what factorial is. Okay. This e is exp or exponent. You can actually go and check its value on Google in case you don't know. And here in the case of Poisson distribution, the parameter is lambda. Lambda means it's a parameter means it actually decides these probabilities completely. So if I know lambda, then I can get this probability. Okay. For example, let us say that number of people visiting a particular ATM. So visiting an ATM in 1 hour, in 1 hour, this suppose follows. So let me use notation for it. So x follows Poisson with say 37 as lambda. Okay, Poisson with 37 as lambda. In the case of Poisson distribution, the mean value or the expected value of that random variable is lambda itself. Okay. So what does it mean? X follows Poisson lambda means on an average 37 people visit that ATM per hour. So suppose I want to compute probability of no person visiting an ATM in an hour. So that will be probability of x equal to 0. So e raised to minus lambda, that is e raised to minus 37. Then lambda raised to the value of interest. So 37 raised to 0 upon 0 factorial. So this becomes e raised to minus 37. Okay. In general, we can compute this for any case. So let me consider an example. Suppose the number of claims received by an insurance company per day has Poisson distribution with mean 7. Okay, so we are talking about number of claims received per day. Okay, X has Poisson distribution with say mean 7, and we want to check what are the chances that there will be more than 15 claims. Okay, because suppose we can handle at most 15 claims. So we want to compute probability of having more than 15 claims. So that would be computed as e raised to minus lambda, lambda raised to k upon k factorial, because this is individual probability of single k. And we want to talk about x greater than 15. So we will talk about values of k going from 16 to infinity. Okay, this is a convergent series. Okay. So probability of x being greater than 15 is this. This is the way in which Poisson distribution can be used. Now, actually, uh, as I said, there are lots of application. For example, suppose you own a call center. So when you own a call center, you will need information on various things because you want to hire operators. So how many operators should you hire? If you hire very few operators, then people will have to keep waiting for very long and then they will be fed up with your service and then they might leave you. On the other hand, if you hire too many operators, then many of them will not be doing any work, they'll just be getting paid because there are not many calls. But you keep losing money. Okay, you keep losing money. Hence, you cannot have very few number of operators or very large number of operators. Okay, what you need is just optimal number of operators. So that can be estimated by using this. So we will try to model the number of calls, and then we will say that okay, if the number of calls has certain mean, then what are the chances of, for example, here, if we say the chances of receiving say more than 10 calls are very slim, then you at a in say given time slot, then you don't need more than 10 operators. Okay. Of course, the actual calculations are much more complicated and sophisticated, because we will also have to worry about the duration of time spent on talking on a phone, etc. So we will need some other distributions there. But in general, Poisson can be used when our possible values are not limited. In principle, higher values are also possible. So in such case, we go for Poisson distribution. So we have studied Bernoulli, binomial, and Poisson distribution. So I hope you can go through some of the examples and make sure that you understand these things. Okay, let me stop here. Thank you.